Hello, welcome back to the playlist of topics on regression models and statistical machine learning. I am Hemakumar Kasala, and as part of this video, we learn the concepts that constitute the initial steps on multiple linear regression model building, namely model estimation and the basic evaluation. In this part of the video, we learn about estimating the model, estimating its coefficients, and learn about arriving at the point estimates and the predicted values for the response variable using the estimated model. We learn about deriving the confidence interval and the prediction interval for the point estimate or the predicted value respectively. Then we learn more about evaluating the model utility using the basic statistical quantities like R-square and adjusted R-square, and the methods like normal probability plots to verify the basic assumption that the model should comply with. Let's get into the video. The first important thing in model building is arriving at an estimated model, since the multiple regression model at the population level is not readily available in almost all cases. The estimated model is a model that uses the estimates in place of the unknown alpha and beta coefficients of the population model. In this lecture, we learn about the least squares method to calculate the estimates. Using the estimated model, we learn about estimating the mean response or a single predicted value for the response variable for a chosen instance of predictor values. Model building involves the following major steps. Choose the predictors to begin with. That decides the number of predictors too. Calculate the alpha and the beta coefficients. Assess the model and check if there is a scope for improvement or reach the best possible fit. If there is a scope for improvement, add, remove or change the predictors and recalculate the alpha and the beta coefficients. Reassess the model and check if there is a scope for improvement or reach the best possible fit. In case there is scope for improvement, redo the steps until you reach a best possible fit. On arriving at a best possible fit, conclude the model with a final set of predictors and coefficients and make the inferences. We will dive into the details of each one of these steps, partly in this lecture and in the following lectures to come as part of this playlist. There are well-defined different possible methods to choose the set of the predictors to begin with, and subsequently refine the predictors list by adding or removing the predictors. We will learn these methods in later lectures. Therefore, as a first step, we focus to understand how we arrive at the alpha and beta coefficients, having decided on which predictors x1, x2, etc. xp to include to begin with. Note, the alpha and the beta coefficients are the coefficients of the population regression function, which are almost always unknown. Therefore, like in the case of the simple linear regression, these coefficients are estimated from a random sample. Accordingly, A, the estimate of the intercept alpha, and B1, B2, etc. BP, the estimates of the beta coefficients, are calculated from a random sample of size n. A random sample of size n includes n records, each of which contain values for p number of independent or predictor variables x1, x2, etc. xp, and one independent variable y as in x11, x21, and so on xp1, y1, x12, x22, and so on xp2, y2, and so on x1n, x2n, and so on xpn, yn. Each record, often referred as an observation in the above set of n records, is drawn from the population in such a way that it is independent of one another, which is characteristic of any random sampling. Like in the case of simple linear regression, the principle of least squares is deployed to calculate the estimates of the coefficients. Least squares method aims to minimize the sum of the squared deviations, denoted by sigma deviation I square over n observations, where deviation I equals yi, the observed value of the dependent variable in the ith observation or the record, minus the estimated response calculated using the estimated regression function for the ith observation or record in the sample. Deviation I equals yi minus a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi, where x1i, x2i and so on xpi are the values of the predictor or independent variables in the ith observation or record in the sample. And a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi in the above equation is the estimated regression function that uses the estimated values for alpha and beta, which are a, b1, b2 and so on bp. Sample data with 22 observations from 22 randomly chosen colleges are shown below, using which we try to arrive at a multiple regression model explaining the relationship between the independent variable y, the 6-year graduation rate, which is the measure of success, and the predictor variables x1, which is the median common admission test score, x2, student related expense per student in dollars, and x3 is an indicator variable equal to 1 if college has only male or female students and equal to 0 if it has both genders. Deviation I for the ith record, for example the record corresponding to the Chadron State College, is calculated as deviation I equals yi minus a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi, where yi equals 0.469, xi1 equals 990, x2i equals $6046, and x3i equals 0, meaning this is the college for both genders. Least squares method works to minimize the sum of the squared deviations, sigma n deviation I square, which is the sum of the squares of deviations for each of n equal to 22 observations, and arrives at the coefficients a, b1, b2 and so on bp such that sigma n yi minus a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi the whole square is the least possible value. Deviation I equals the observed response value yi minus the estimated response value yi hat, where the estimated response value yi hat is also called as the estimated mean or the predicted response value, is calculated using the estimated regression function for every observed data in the sample, as in yi hat equals a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi. Least squares method uses the sum of the squared deviations, sigma n deviation I square, as a measure to judge the fit of the estimated regression function to the observed or the sample data. The estimates a, b1, b2 and so on bp of the population regression function coefficients alpha, beta 1, beta 2 and so on beta p are those that minimizes the sum of the squared deviations to a least possible value. Please recall, in case of simple linear regression formula, the coefficients could be derived as shown below, as there were only two unknowns, intercept a and slope b. Deriving the same for p plus 1 coefficients where p plus 1 is greater than 2 becomes mathematically cumbersome. However, the statistical or machine learning software libraries are programmed to handle this complexity, and render these coefficients when they are invoked. Invoking one such software tool Minitab in this case on the college data, we get the following results in the form of a set of tables. Let's examine the estimated multiple regression function with three predictor variables from the college data table. Coefficients of the estimated regression function arrived are intercept A equals minus 0.391. The estimated coefficient for x1, which is the median common admission test score B1, equals 0.0007602, which means the rate of change in the estimated mean response value y, the 6-year graduation rate, which is the measure of the success for any college, equals 0.0007602 for every single unit change in x1, the median common admission test score, when the rest of the predictor values remain unchanged. The estimated coefficient for x2, that is student related expense per student in dollars, B2, equals 0.000007, which means the rate of change in the estimated mean response value y equals 0.000007 for every dollar change in x2, that is student related expense per student in dollars, when rest of the predictor values remain unchanged. And finally, the estimated coefficient for x3, the indicator variable that identifies whether a college has only male or female students or both, B3, equals 0.125, which means the rate of change in the estimated mean response value y for any college that has only male or female students and not both is augmented or corrected by a value equal to 0.125 compared to the mean value y for any college that has both genders, when rest of the predictor values remain the same. The estimated regression function for the multiple regression model with three predictor variables is y hat equals minus 0.391 plus 0.00076 multiplied by x1 plus 0.000007 multiplied by x2 plus 0.125 multiplied by x3. As discussed in the case of simple linear regression, the estimated regression function is primarily used to estimate the mean response value y, in this case the 6-year graduation rate or the success rate, which is also called as the point estimate, or predict the value of a success rate of a single college, also called as the point prediction, when the values of the three predictor variables are chosen. Accordingly, choosing the following values for each of the three predictor variables: x1, the median common admission test score, equal to 1000, x2, the student related expense per student in dollars, equal to 11,000, and x3, the indicator variable for a co-ed college, equal to 0, we arrive at point estimate of the mean value of success rates, or the point prediction of the success rate for a single college, equal to minus 0.391 plus 0.00076 multiplied by 1000 plus 0.000007 multiplied by 11,000 plus 0.125 multiplied by 0 equals 0.4462. Recall our learnings from simple linear regression models that the discussions on point estimate or predicted value is not complete without calculating the confidence interval or the prediction interval respectively for each of them. In this lecture, we focus on learning how to derive these intervals. Recall our learnings from simple linear regression models that for a chosen single predictor value, confidence interval or prediction interval equals point estimate, or in other words the predicted value, plus or minus t critical value multiplied by standard deviation, where point estimate or the predicted value, both actually mean the same, is calculated using the estimated regression function for that chosen single predictor value. T critical value is taken from the T statistic table for a chosen value of the confidence level, say 90% or 95% or so. And the standard deviation is an estimated value calculated primarily using the standard deviation SE from the residuals out of the current sample, and its values are calculated differently for confidence interval and the prediction interval. The confidence interval and the prediction intervals in case of multiple regression models are calculated using identical methods. Let's focus on the confidence interval first. Confidence interval equals point estimate plus or minus T critical value multiplied by standard deviation, calculated for a selected instance I of the predictor variables, as in x1i, x2i, and so on xpi. Confidence interval at I equals point estimate at I plus or minus T critical value multiplied by standard deviation at I. Confidence interval at I equals yi hat plus or minus T critical value multiplied by standard deviation at I, where yi hat is the point estimate of the population mean as per the unknown population regression function. By substituting the values of x1i, x2i, and so on xpi in the sample or estimated regression function, as in yi hat equals a plus b1 multiplied by x1i plus b2 multiplied by x2i plus and so on plus bp multiplied by xpi. T critical value is taken from the T statistic table for chosen values of the confidence level, either 90% or 95% or so, like in the case of simple linear regression. And the degrees of freedom df equals the sample size n minus the number of predictors p plus 1. 1 minus confidence level divided by 100 equals alpha is also called as the level of significance. And standard deviation given by SE multiplied by square root of xi transpose multiplied by x transpose multiplied by x whole inverse multiplied by xi is the estimated value calculated using the estimated standard deviation SE of the residuals out of the current sample, and xi is a vector given by xi equals 1, x1i, x2i, and so on xpi transpose, and x is a matrix of n records, each containing set of p predictor values from the sample as shown below. Note that xi is the transpose of the ith row or record in X. Though calculating the standard deviation using this expression looks complex, in practice it is provided by most of the software tools implementing the multiple regression as shown in the snapshot below. We take a sample data of size n equals 38 college students to understand the calculation of confidence intervals and subsequently the prediction intervals. The research question under the study is whether the brain size and the body size play a significant role in deciding the intelligence IQ of a student. We fit a multiple regression model and pay attention to only the confidence interval and later the prediction interval outputs by the model. For the chosen predictor values, brain size equal to 90 and height equals to 70, Minitab estimates the mean performance IQ score yi hat as 105.64 and the confidence interval considering 95% confidence level and degrees of freedom equal to sample size of 38 minus 2 plus 1 is between 98.24 and 113.04. That means we can be 95% confident that the mean performance IQ score of all college students with brain size equal to 90 and height equal to 70 is between 98.24 and 113.04. Since SE in the expression for calculating the confidence interval equals square root of mean regression sum of squares MSR, which equals square root of regression sum of squares SSR divided by n minus p plus 1, where SSR, like in the case of simple linear regression model, equals sigma n yi minus yi hat the whole square. The confidence interval is large when mean residual sum of squares MSR, that is the variance of the residuals, is large, and is small when MSR is small. That is because variance in the residuals MSR is a quantity that roughly determines the swing in the slope coefficients, which in turn determine the possible swing in the difference between the estimated mean and the population mean. Refer detailed explanations on this topic in the lectures on simple linear regression models. Confidence interval is small when the sample size n is large, and is large when n is small. The reason is, larger the sample size, lesser is the deviation between the estimated regression function and the population regression function, thus resulting in reducing the confidence interval. Confidence interval is large when t critical value, that is the confidence level, is large, and is small when t critical value is small. More confident that one wants to be to locate the population mean within the interval, larger or wider is the confidence interval. Square root of xi transpose multiplied by x transpose multiplied by x inverse multiplied by xi in the confidence interval implies closer is xi to the mean of the predictor values in the sample, smaller the confidence interval is. Farther xi is from the mean, larger is the confidence interval. This is by virtue of the slope of the estimated regression function as against the population regression function, though visualizing these slopes in multiple regression models is complex. The difference between the slopes results in larger gaps between the estimated and the population regression lines at predictor values away from their mean as against the predictor values closer to their mean. In order that the confidence interval arrived using this method or calculation is reliable, only when the following assumptions about the error distribution with respect to the population regression function are by and large met. We already discussed these requirements as part of simple linear regression models, and the same applies here. The distribution of error E at any particular value of x is normal. The distribution of E at any particular value of x has a mean mu e which equals 0. The standard deviation sigma for the distribution of error E remains the same for any value of x. The random deviations E1, E2, etc. En across observations at any particular value of x are independent of one another. For confidence interval, the assumption that the error distribution should be normal can be a bit largely relaxed, as the method for calculating CI yields fairly good results even when this assumption is not met with. Let's turn our attention towards prediction intervals now. The prediction interval, on the other hand, is given by prediction interval equals point prediction plus or minus t critical value multiplied by square root of mean residual sum of squares plus SEI square, where point prediction is the same as the point estimate, which equals yi hat. SEI denotes SE multiplied by square root of xi transpose multiplied by x transpose multiplied by x inverse multiplied by xi, and t critical value is the same as that described for the confidence interval. The standard deviation part in the above equation, that is square root of mean residual sum of squares MSR plus SEI square, has two parts. The first one being MSR, that accounts for the variance in a single y value prediction yi hat with respect to the mean y value at I, yi bar, and the second one SEI square, that accounts for the variance in the point estimate yi hat with respect to the population mean at I, that is yi bar. Like in the case of confidence interval, any software tool like Minitab calculates the prediction interval as well and presents. For the same predictor values, brain size equals 90 and height equals 70. Minitab predicts the performance IQ score yi hat as 105.64 and the prediction interval considering 95% confidence level and the degrees of freedom equal to sample size 38 minus 2 plus 1 is calculated and is shown between 65.35 and 145.93. That is, we can be 95% confident that the performance IQ score of an individual student whose brain size equals 90 and height equals 70 is between 65.35 and 145.93. Like in the case of confidence interval, the following four assumptions about the population error distributions should be by and large met. Unlike the confidence interval, the calculation of the prediction interval depends strongly on the assumption that the error distribution is normal. Here are the formulae for calculating the confidence interval and the prediction interval. The difference between the two intervals is that the prediction interval includes the mean residual sum of squares MSR in the standard deviation calculation. Therefore, like in the case of the simple linear regression, the prediction intervals are larger than the confidence intervals at any given instance of the predictors xi. Both prediction interval and the confidence interval is least at the instance of the predictors that is close to the mean of the predictor values calculated from the sample. Also, the influence of sample size n, mean residual sum of squares MSR, and t critical value or confidence level on prediction intervals are the same as that we discussed under confidence intervals. That concludes our study on confidence and prediction intervals, and let's move over to evaluating the model's utility. A large part of the multiple linear regression model building goes into verifying its utility, evaluating how good the model is. There are a lot of statistical quantities and tests that are available for verifying the model utility. We make a beginning in this lecture and learn about a few fundamental statistical quantities and methods like R-square, adjusted R-square, and normal probability plots. How useful is a model? The answer to this question lies in how accurate are the predictions for y values using the estimated regression function. In other words, how close are the predicted y values y hat to the observed y values in the sample? Do each of the predictors chosen explain the variation in y values in the sample faithfully? Do they individually contribute? In other words, are the coefficients of individual predictors statistically significant? Are the number of predictors optimally chosen? In other words, are there too many predictors resulting in more fitting? Are the correct predictors chosen among the qualifying predictors while keep the number of predictors optimal? In this lecture, we take a look into the first question. How accurate are the predictions of y values using the estimated regression function? That is, how close are the predicted y values y hat to the observed y values in the sample? Please recall, in case of simple linear regression, we use the following summarizing quantities to judge the accuracy in the fit. Residual sum of squares denoted by SSR, total sum of squares denoted by SST, coefficient of determination denoted by R square. These statistical measures are useful in multiple regression models as well. And let's understand how we derive them in multiple regression case. Deviation between an observed value yi and the corresponding predicted value yi hat is the residual. Residual I equals yi minus yi hat. Referring back to the college data example and picking an observation or record from the sample randomly and substituting the values for x1, x2, x3 in the estimated regression function, we get yi hat equals minus 0.391 plus 0.00076 multiplied by 1170 plus 0.000007 multiplied by 13154 plus 0.125 multiplied by 0 equals 0.590278. Residual I in this case equals yi minus yi hat equals 0.545 minus 0.590278, which approximately equal to minus 0.0453. Substituting the values for x1i, x2i, x3i each time in the estimated regression function for every observation in the sample, we get y1 hat equals minus 0.391 plus 0.00076 multiplied by x11 plus 0.000007 multiplied by x21 plus 0.125 multiplied by x31. y2 hat equals minus 0.391 plus 0.00076 multiplied by x12 plus 0.000007 multiplied by x22 plus 0.125 multiplied by x32 and so on, and yn hat equals minus 0.391 plus 0.00076 multiplied by x1n plus 0.000007 multiplied by x2n plus 0.125 multiplied by x3n. Residuals from the sample are the differences between the observed values of the response variable yi and the predicted values yi hat for each of the observation, as in y1 minus y1 hat, y2 minus y2 hat, and so on, yn minus yn hat. Note, some of these residuals in a least squares fit shall be 0 excepting for rounding errors, which is the same as in the case of simple linear regression. These residuals provide the basis to arrive at various summary quantities that help qualify the model's utility that we discussed just a while ago. Residual sum of squares SSR, total sum of squares SST, coefficient of multiple determination R square. Note the inclusion of the term multiple above and the uppercase R used instead of lowercase r. We'll discuss the reason just a while later. Residual sum of squares SSR equals sigma n yi minus yi hat the whole square, where yi is the observed value in the ith record or the observation, yi hat is the predicted value using the estimated regression function for the ith observation, and n is the sample size. This is not different from the way SSR is calculated for simple linear regression, except that the predicted values are calculated using multiple predictor variables. Total sum of squares SST equals sigma n yi minus y bar the whole square, where y bar is the mean value of the observed y values from the sample. The number of degrees of freedom associated with SSR df equals n minus p plus 1, since p plus 1 observations out of n, the sample size, are used up in estimating p number of slope coefficients, that is the bi's, and one intercept a. Please recall E being the error in the population left undescribed by the population regression function. The standard deviation of error E is denoted by sigma. Since sigma is unknown, its variance sigma square is unknown as well. The variance sigma square is therefore estimated from the sample, denoted by SE square equals SSR divided by df, which equals SSR divided by n minus p plus 1. The estimate of the standard deviation of error E sigma is given by SE equals square root of SE square. While SST is the total variance in the observed y values in the sample, SSR is the variance in the observed y values left undescribed by the estimated regression function. Coefficient of multiple determination equals variance in observed y values described by the estimated regression function divided by total variance in the observed y values. The above definition is pretty much the same as in simple linear regression, except for the inclusion of the term multiple in the name. Coefficient of multiple determination denoted by R square therefore equals SST minus SSR divided by SST, which equals 1 minus SSR divided by SST. Note that the notation for coefficient of multiple determination is capital R square and not lowercase r square. In case of simple linear regression, the coefficient of determination equals R square, where R is the correlation coefficient as well between the dependent variable y and the single independent variable x. Whereas in multiple linear regression case, since there are more than one independent variables, R square cannot be used and hence an independent notation capital R square is used instead. Getting back to the college data problem and taking a look at the output tables generated by Minitab, we have residual sum of squares SSR equals 0.12833. Number of degrees of freedom DF associated with SSR equals 18, which is sample size minus the number of predictors 3 plus 1, which equals 22 minus 4, which equals 18. Therefore, estimate of the variance sigma square SE square equals SSR divided by DF equals 0.12833 divided by 18 equals 0.007. Estimate of the standard deviation sigma SE equals square root of SE square equals square root of 0.007, which equals 0.0844346. Total sum of squares SST equals 0.92318. Number of degrees of freedom DF associated with SST equals 21, which is sample size minus 1. 1 stands for the mean, equals 22 minus 1 equals 21. R square equals 1 minus SSR divided by SST, which equals 1 minus 0.12833 divided by 0.92318 equals 1 minus 0.139, which equals 0.861. The value 0.861 or in percentage 86.1 for R square mean that 86.1% of the total variance in Y is described by the estimated regression function. 13.9% of the total variance in Y, which is SSR divided by SST in percentage, is left undescribed by the estimated regression function. A high value for R square and a low value for SE will be the metric one would aim at. This can be achieved in a way by merely increasing the number of predictors, even if each of the additional predictors show insignificant relationship individually against the dependent variable. But a model with bloated number of predictors can seldom be generalized for the population. In other words, too many predictors will result in overfitting and thus give a desired R square and a low value for SE, but will fail to describe the population. Such a model will fail to describe another randomly chosen sample from the same population. Therefore, the increase in the number of predictors to the model should be checked against tangible increase in R square and fall in SE. The additional quantity that helps to judge the gain in R square and SE while adding predictors to the model is adjusted R square. Adjusted R square equals 1 minus n minus 1 divided by n minus p plus 1 multiplied by SSR divided by SST. Adjusted R square has a factor n minus 1 divided by n minus p plus 1. N minus 1 divided by n minus p plus 1 is always greater than 1, and increases as the number of predictors P increase. Therefore, the ratio SSR divided by SST subtracted from 1 in case of R square is increased to n-1 divided by n P plus 1 multiplied by SSR divided by SST in adjusted R square, resulting in adjusted R square value that is always less than R square. As long as the increase in the number of predictors P bring tangible reduction in SSR, the adjusted R square remains close to the R square value. Arithmetically, increase in P is compensated by the fall in SSR. Steeper fall in adjusted R square as against R square indicates that the predictors added are introducing overfitting, and therefore either new set of predictors should be tried or settle with the model with current set of predictors. Getting back to the model results on the college data, we see adjusted R square equals 83.8%, which is fairly close to R square, which is 86.1%. And therefore, the number of predictors P equals 3 does not introduce overfitting concerns for the model. Thus, adjusted R square along with R square and SE provides a means to verify if the model is simple, meaning not with excessive number of predictors, the predictors that are interpretable and understandable, that finally explains as much of the variance in the response Y. Note, adjusted R square is one among the many summary quantities that help check and improve the model utility. We will discuss the rest of the means and measures in later lectures. Like in the case of simple linear regression, normal probability plots are used to verify the normality in the distribution of the residuals, which is one among the 4 requirements for the error E. As we learned already, the standardized residuals are plotted against the normal scores in a normal probability plot. Most of the standard softwares can provide standardized residuals to facilitate the normal probability plot. Here is the Minitab output with standardized residuals, calculated on the college data for each of the 22 observations in the sample. Here is the normal probability plot using the above standardized residuals. The graph looks fairly straight, confirming that the assumptions about the error distribution is largely met. That brings us to the end of the discussion on multiple linear regression model estimation and basic evaluation. See you back soon with the next lectures on this topic on multiple linear regression models. Bye for now.